Today I'm very pleased to have Dr. Jiren Lin to give us this colloquium talk. So let me brief introduce the Professor Lin. Professor Lin is one of our alumni. He graduated from Department of Physics in 1993. So after spending 2 years in the Army,
Air Force.
Air Force. Oh wow. Okay. In the Air Force, and then he went to University of Edinburgh for his PhD degree. So then he spent 4 years there and obtained his PhD in 1999. Okay. Then afterwards, he went to several institutes for his postdoctoral research. One is the University of Kentucky in 1999, same year. Then he went to University of Southampton for 4 years. And then he went to this University of Seattle. Washington and Seattle, sorry. In 2003 to 2006. That is a very nice institute, especially for nuclear physics and particle physics. Then he went back to Jiao Tong University as a faculty there. So his expertise is on this lattice field theory. It's a high energy, especially is in the QCD and flavor physics. Okay, let's welcome Professor Lin.
So first I'd like to thank our chairman, Hao-Ti, and all the other colleagues who invited me back to my alma mater to give this talk. It's very nice of you, thank you. And so today I will report on something that's not QCD, but something that I spent quite a bit of effort during the past decade, which I will continue in the years, in the coming years in the future. Okay, so let me put on this slide. So this is some kind of standard slide that you will see if you go to DOE, Department of Energy website. So we know that the core question in particle physics to find the origin of the universe and also the building blocks of the universe. And this kind of diversifies into 3 frontiers: the energy, intensity, and cosmic frontiers. They all have their own, special questions to answer, which are directing towards this core problem in particle physics. And today I will focus on the energy frontier here. And especially, I would like to address this question of the origins of mass, and I would like to try to introduce to you what kind of role lattice field theory can play in this game of looking for the endeavor of looking for the original mass. So then, of course, to put lattice field theory in context here, let me also put on this slide. This is our question now. And of course, we need experiments, since physics is an experimental science. So experiments are always the most important thing. But then we also need phenomenology, which would actually guide us about the interpretation of experimental results. So that's also something very important. On the other hand, the modern particle physics phenomenology models are all constructed using quantum field theory. And therefore, the study of field theory is also very, very important, because we want to identify viable models which can be used to build phenomenological models which can interpret experiments successfully. Okay? And that's where lattice field theory comes into this game. Okay? So this is going to be my focus today. So the outline of this talk is that I will, since there are students here, and I will then briefly introduce to you how the origin of mass is explained in the standard model of particle physics. and I'll tell you why it's not enough. And then I'll tell you why lattice field theory can play a very important role in going beyond this standard model of particle physics. And in particular, I will cite two examples here. One is the study of the Higgs-Yukawa model, and the other one is the treatment of Higgs as a downstate of other more fundamental particles. And then towards the end of this talk, I will introduce to you some new techniques that we picked up from our condensed matter physics colleagues like Ying-Zhe here. And this was actually partly inspired by this BSM, Beyond the Standard Model studies on the lattice as well. Okay, so that's the plan of the talk. So let's start from the standard model Higgs. So this is the black book in Peter Higgs' office in Edinburgh. He wrote this a couple of years before he got the Nobel Prize for some press interview. And in his theory, the Lagrangian looks like this. You have the complex scalar field. This is just his illustration by using a slightly simpler model compared to what actually went into the standard model. But this is enough to just illustrate a key point. So now you have this one copy of complex scalar field, and it couples to this gauge fields. This F mu nu is the familiar gauge field that we all learned about in electrodynamics. And then through the covariant coupling, okay, so the Higgs field will couple to this gauge field here. But the most important thing is that there's this Higgs potential, which plays the key role of giving masses to elementary particles, or some elementary particles at least. So let me elaborate a little bit on how this works by looking into this potential a little bit. Yeah. So this potential involves two terms. One is the quadratic term, and the other is the quartic term. Okay? And of course, the quartic coupling lambda always has to be positive for the potential to be bounded. On the other hand, this mu square doesn't have to be. Okay? So there's something called spontaneous symmetry breaking that's implemented in the following way. So when mu square is larger than 0, you have this hyperbolic type potential that is not very interesting, and you have your unique ground state here. And if you turn on quantum corrections, quantum fluctuations will be around this unique ground state here. Now, on the other hand, if you turn this mu square to be negative, the potential develops this wine bottle shape, or the Mexican hat shape, okay, where you have this infinite number of degenerate continuous ground states, okay, and this distance here is parameterized as V. It's called V for a specific reason, because in quantum theory this is identified as the vacuum expectation value of this scalar field itself. Okay, so that's why it's called V. And if you really compute it, some simple algebra for this illustrative example will show you that it actually is equal to this number. Okay, and armed with that, you can parameterize your scalar field, this complex scalar field, in this way. That means it's actually fluctuating around this bottom. First, you fix one unique vacuum here. And that's why it's called spontaneous symmetry breaking, because this symmetry, when you rotate along this real and imaginary plane, is still preserved in the potential. But you have to choose your unique ground state, and that breaks the symmetry in the state and the spectrum itself. Okay. And you see that once you parameterize your field this way, then you have two fluctuations in directions. One is the longitudinal part, okay, that costs energy, and that's why you have some massive mode, which is identified as a Higgs particle in this context. And you also have another mode that's taking you along this valley, which does not cost any energy at all, and then therefore you have something called the Goldstone boson, which is massless. So this is roughly how it works. To generate this VEV first, and then if you go back to the Higgs theory, you see that it couples to the gauge bosons to this covariant derivative, and that would actually in turn generate masses for the W and Z boson. In the standard model, and of course the mass would look like some coupling constant or interaction strength times the the VEV. And furthermore, you can also push this forward to try to explain the origin of origin of the masses for some fermions in the standard model by introducing these Yukawa type interactions. This psi L and psi bar L and psi R are just left and right-handed fermions. And then once you introduce these couplings, you can actually easily show that the fermion masses will be proportional to the Yukawa coupling times the VEV. So the VEV plays a very important role, and therefore this spontaneous symmetry breaking in the Higgs potential is very, very important. Yep. Okay. So how does this work? How is it doing? How is this kind of scenario doing? Good. Okay. The good thing is that if you look at the experimental status, okay, this is one of the many slides that I took from the CCMS website. You see that the measurements of a lot of decay modes for the Higgs, okay, is they are all consistent with the theoretical prediction. So these yellow bands are just the ratio between the experimental and the theoretical estimates of the cross section. You see that everything is very, very nicely fit into theoretical, into experimental measurements by applying this model. And this is just one of the many examples that you can find if you look through the CCMS or Atlas websites. You can see many, many plots like that. The gist is the standard model is totally compatible with the experiment. Okay. So to summarize, so what we know from the Large Hadron Collider is that Higgs was found, and it's 125 GeV, and the experimentalists have been working very, very hard to look for new physics, and they've searched up to about 2 TeV, which is one order of magnitude up from the Higgs mass, and no new physics has been found. Okay? All we know is that if there's any new physics, the Higgs boson has to be very, very light compared to anything that you can find. So then the question is, why bother, right? Standard model is working very, very well. It explains everything. So why are we still looking for physics beyond the standard model? Now, for people who work on quantum field theory, this is actually a very exciting result because that presents a big puzzle that you want to solve. The bad, okay? Why is this bad? Why is this leading to some questions that we want to answer? So it's good and bad, actually. To understand this issue, let me, again, briefly introduce this notion of running coupling constant for at least the students who may not have taken quantum field theory course. And to put it in a very simple way, quantum field theory is actually born out of the marriage of special relativity and quantum mechanics. So if you put these two very nice and beautiful subjects together, you can actually have some virtuality in your vacuum. And therefore, if you put, say, a negative charge here, it would actually polarize the vacuum. And you actually see a lot of polarized pairs of positive and negative charges in the vacuum. And therefore, imagine you have a particle traveling like that, then this guy will not see really this charge. It will see this charge as being screened by all these guys around it, right? So it depends on how energetic this guy is. It could actually get closer and closer to this, okay? And then it's going to see this the strengths of the interaction very differently. In other words, the interaction strength or coupling constants in quantum field theories will actually change with distance or energy scale. Okay? So that's a very important notion. Now, let's come back to look at the Higgs potential. Remember, this lambda is the quartic coupling, and it plays a very important role as well, right? Because without a quartic coupling, you only have the quadratic coupling, and then there's no interesting thing in the Higgs potential. Right? You need lambda because we bound it, and mu squared could be negative. Now, let's assume that the standard model will give us the Higgs mass here, and the Cordy coupling will take this value of red lambda, and let's assume that the standard model would actually be valid up to some energy scale capital M bar. Okay, and beyond this M bar, you have some new physics emerging, and from this new physics theory, once you discover it, let's say you can actually compute everything that you observe in the experiments, and you can compute what's happening in the standard model. And let's say that the Higgs Cordy coupling is lambda hat at this scale. This is the scale where you match your standard model onto something more fundamental. So the question is, where is this big lambda? So where is this big M? Okay, can I push this big M to infinity? If I can, and the standard model still is problem-free, that means the standard model can actually be our fundamental theory. But if I cannot, then the standard model must fail. Okay, at some stage. So let's try. Now look at this red thing. When I start pushing up this capital lambda hat, you see the way that the Higgs coupling, the Cordy coupling runs is that it gets smaller and smaller if you hold this lambda hat fixed. So that means once you push this M hat to infinity, this red lambda goes to 0. And then the theory becomes free, it's not interactive, it's not an interesting theory. And therefore it's trivial, it cannot explain anything at all. So that means physics beyond the standard must be waiting for us out there somewhere. Okay, just from the internal structure of the theory itself, we know that the standard model cannot be complete. So we have to look for physics beyond the standard model. We're forced to do it because we know it's not right somewhere. Okay? So we cannot be happy with the standard model itself. Now, you can turn this argument around. You say, okay, so let's say that someday experimentalists will actually measure this red lambda, and let's see if I hold this fixed and I just push up this capital M hat, what's going to happen to this guy? Okay, I can ask this question in another direction, and then you see this big, this lambda bar actually grows. Okay, that actually means at some stage things get non-perturbative. The Bayesian theory just cannot tell you anything at all. If you want to look for new physics, somehow, at some stage, it's very likely that non-perturbative physics would actually come in and play an important role like that. Okay? Now, the argument. This is something that some of you may actually have heard lots at talks, is the naturalist problem or hierarchy problem. So, if you look at the Higgs potential like that, okay, if you turn on quantum corrections, then things fluctuate around the bottom of the potential, and then modes at different energies would actually start mixing, and it so happens that in this case, some modes at this M bar will mix with this U square parameter to cancel, to have a big cancellation to give this mx squared. So this is mc squared. So there's a huge cancellation going on. Okay? And the reason why I call this ugly is actually there's nothing wrong with it. Okay? It's just not beautiful. We don't like it. But there's nothing fundamentally wrong about it. And of course, you don't like it, you want to search for something new, and then huge cancellation signals that something non-perturbative has to come in at some stage. Okay? So then here comes lattice field theory, which is the most reliable tool for dealing with this non-perturbative physics and quantum field theory. Any questions, especially from students so far? No? Okay. I hope I haven't lost all of you. Okay. Okay. So lattice. So lattice is, you put your space-time, continuous space-time on grid, okay? And what happens is that you put the matter fields, meaning fermions and scalars, on the sides. And you put your gauge fields on the links. Okay? And the reason is, of course, the gauge fields are parallel transports. Yeah? And the lattice spacing here is denoted by A. And what's good about this is that in quantum field theory, you have infinite number of degrees of freedom, but then if you discretize your space-time like that, and you put everything in the four-dimensional finite box, then the number of degrees of freedom becomes finite. It's still very large, but it's finite. And that actually allows you to do numerical simulations, numerical calculations to compute what you want. So the fundamental thing that we're dealing with is this partition function. Of course, you can put in operators, quantum mechanics operators here to compute correlators and matrix elements, for example. But you know, the starting point is to understand how to compute this partition function. And very often we have this gauge field action and the scalar field action, and the fermion fields in all or in most theories that we deal with so far are actually bilinear in fermions. So which means you can actually perform this Gaussian-like integral first, okay? Else it's actually hard because fermions are anti-commuting objects. It is a bit more difficult to deal with on the computer. So what you do is you integrate out these fermions, and it gives you this determinant of this matrix, which represents this fermion action here. And then once you turn this partition function into this form, you have Boltzmann distributions convoluted with this determinant, and then you can actually perform Monte Carlo simulations by using techniques like importance sampling to get these configurations of gauge fields and scalar fields, and try to compute what you want.
So why the matter field including scalar here?
That's just general.
And why you cannot put scalar in the links as a gauge field? It's a field. X is a source of field.
Right, but the scalar field doesn't know the direction. It's a scalar.
Mm-hmm.
The gauge field knows the direction, right? So the gauge field actually carries the Lorentz index mu, right? Okay. So that's why you can put it on the link. Once you put it on the link, you have to specify the direction. But scalar, by definition,
because
doesn't know this.
Because the space time.
Yes.
Okay.
Yeah. So you notice that this is actually very similar to partition functions in statistical physics, right? So in this way, we're actually speaking a very similar language with those who actually do, say, quantum Monte Carlo simulations in statistical physics. And what's even more is that we particle physicists like to work in a continuum space-time, okay? Unlike condensed matter physicists who actually deal with lattices for real, we're actually forced to take the continuum limit. Yeah. In other words, we want to take the lattice spacing to 0. And if you think about how you would do this, lattice spacing goes to 0 means when you multiply any number, or any mass, which becomes a dimensionless number, it goes to 0 if you have finite mass. And also any long distance effects as characterized by the correlation length C in your system would actually diverge in comparison with this lattice spacing. Okay? So, which means the continuum limit or continuum limits in a lattice field theory are actually where you can actually see second order phase transitions. Okay? So in this way, I can speak from my own experience. Whenever we actually we want to do a new simulation for some more exotic theories on a lattice, we really do spend a lot of time looking for second order phase transitions. And we want to work around that. Yeah? In other words, critical phenomena is actually something very important for lattice studies. Okay? So that's all I want to say about lattice field theory, because anything beyond this will get a little bit technical. Okay. So then let me illustrate the use of lattice field theory in a couple of things that you can study on lattice and what I have done in the past decade as well. The first thing is we asked the question, is there any new physics in the Higgs-Yukawa theory? What does that mean? The Higgs theory and the Yukawa coupling, well, those are standard model things, right? So what do I mean by this? Now let's come back to look at what we have. We have the Higgs potential, which will generate this wave and which will give masses to the gauge bosons. And we also have the Yukawa coupling, right? Which will give some, which will give masses to some fermions, to the majority of the fermions in the standard model. And if I plot, whatever you want to compute, okay, and where people actually have gone to compute things in lambda and y is we call it coupling, and this mu square, and for some reason we Lattice people want to parameterize this as 1 over mu square in this very weird way. But this y-axis is basically just 1 over mu square. Can you regard as that? So if you say that this is the region where most phenomenologies actually have gone and tried to compute things to compare with experiments and try to make predictions about new physics and so on, you soon realize that okay, now if a Lattice person like me are coming to this game, I want to start studying this field theory. What do I do? A very prominent physicist, Giorgio Parisi, once made this advice to all of us. Say, let me describe a typical computer simulation. First thing to do is look for phase transitions. Okay, so you follow this very nice suggestion from a very prominent physicist. What do you find? You find that this region where people have actually performed a lot of calculations in phenomenology is a very small corner in a phase diagram of the Higgs-Yukawa model. Okay. The model is actually a lot more complicated than what we thought. Huh? So, I don't have time to really go through all the details of this phase diagram. This is roughly what we know at this stage. Let me say this is rough. This is rough knowledge of this phase diagram, except for these 2 lines. Okay, and these lines signals where we may have found phase transitions. And are these first order phase transitions or are these second order phase transitions? We're confident that here and here, the solid lines are second order phase transitions. Here and here, they may be first order or second order phase transitions. And you have furthermore transitions here. And of course, particle physicists were interested in the area where this VEF, Higgs VEF, is non-zero, so it's around here. Okay? And then of course, if you ask condensed matter physicists, they may be very interested in these antiferromagnetic phases, where it is a staggered magnetization, or staggered VEF is non-zero, where this eta is just 1 and minus 1 alternating between lattice sides. Yeah? So you see that this phase structure is a lot more complicated than what we thought to start with. Okay? And how much do we know this? There's a gray area we know very little about. Yeah? So studies have been made, and progress has been made, but you see this phase space, this diagram is immense. So it really would take a lot of more efforts and dedicated efforts to go and pin down this phase diagram even more. So let me summarize the recent progress on the study in this direction. So the study of the phase diagram, as I said, is a very challenging task. But I think it's a very important task because if you say that the standard model is all we have, you have the Lagrangian, and you can't just be happy with the perturbative definition of the theory. You want a non-perturbative definition of the theory. And to do that, you know that the careful study of the phase diagram is essential. Okay? So it's hard, but it has to go on. And I myself have actually been involved in some recent works in this direction. Like we've actually devised various methods that we learned from condensed matter physicists to try to look for scaling behaviors, to look for new phase structures. And for those who know a little bit about the renormalization group, we seem to be finding some hints about the possible existence of new fixed points. That would actually be interesting if we can confirm it in the future. Right now, our data are still not good enough to do that, but we've actually done quite a bit of work in the analytic part to develop the tools, and also we have some preliminary or exploratory rather numerical results, which are telling us that this possibility cannot be ruled out. And this Syracuse group also studied this theory, and they found something very exotic. They found that in this gray area that I shared from the previous slide, some new kind of condensates may actually appear. And they claim that some 4 fermion condensates may actually appear. Again, this was done at kind of smallish lattices, so further studies will have to go on. And also, in the early days, people also try to explore this phase diagram with more primitive tools of lattice calculations back then, and they found the possibility that there will be first order phase transition. Okay, and you can actually think of making this phase diagram even more complicated or less complicated. For example, you can take away the Yukawa coupling, and you can add a second copy of Higgs doublets to make it 2 Higgs doublet model, and try to study the phase diagram and see where you can actually have viable theories which can allow you to push up your matching scale of new physics, much higher, and so on and so on. So this is kind of fun. Okay. And in our group, we've also done an extension to this Higgs-Yukawa theory by adding this λ6 operator to the theory, and just to show you that we actually got some interesting phase diagrams, some changes in the phase diagram compared with the theory without this λ6, and you see that we clearly see some hints of these are not hints already. These are actually something very, very different, because we actually saw this de-riskless, for example, to tell us that we see first order phase transitions here. But of course, this is something you would expect, right, from your study of this Landau-Ginzburg theory. If you in condensed matter physics, if you ask these kind of interactions, you're going to get first order phase. But the question is, can you actually push this cutoff scale or this big n bar to very high still in this kind of theory? And the reason why this is interesting, of course, is that this guy can actually signals, or can actually be a prototype of or an effective operator that you can put in to represent the physics plan standard that you may be looking for in the future. Okay, so that's about it that I wanted to say about the Higgs-Yukawa model. That's the first example for the lattice endeavor, looking for physics beyond standard model. Any questions or comments? No? Okay, good. So,
excuse me,
sure.
your previous plot, the lambda is small and negative. What does that mean?
Oh, good. Thanks for this point. Oops. Lambda 6 has to be positive. So the potential is bounded.
Okay.
And then you can turn this lambda and mu square positive or negative as you like, because as long as the potential is bounded, it's fine. Yeah. So this is done at lambda 6 equal to this, and the Yukawa coupling is set to reproduce the top values. Yeah.
It doesn't appear in this plot.
Sorry?
Why does not appear in this plot?
Oh, y is fixed.
Fixed.
Y is fixed to be to reproduce the top quark mass. Y times VEV is the top quark mass in this case. Well, VEV means 246 GeV.
So you're saying actually symmetry breaking is coming from the dimension
6
high
operator.
dimension.
It's a possibility. Yes, of course. Yes. So if you have new physics, which can be wrapped up, right? Effectively, like this operator, this is one option. So this is why this is quite fun. Yeah. 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 I guess this also signals that. Well, thanks George for bringing up this good point. So, I think this is also signaling that we really don't know that much about the Higgs potential. Okay. So, if there's no further comments, let me change gear to introduce to you another research direction that has been going on in the Lattice community in the search for physics beyond the standard model. Higgs as a bound state. Okay. I have to say that there are two main themes in this direction. So, because of the time constraint, I will just introduce one of them, which is more recent these days. If someone is interested, or someone is asking, I can show you another stream of this line of research in my backup slides later. So, this is what we had in the standard model, right? We don't want this. We want it anymore. Just scrape it. We have a different way of generating electroweak symmetry breaking and masses for these elementary particles. We introduce, instead of the standard model Higgs potential and the Higgs sector, or the Higgs color sector, we introduce new strongly interacting fermions and gauge fields. So it's gauge theory, okay? And in particular, we have non-abelian gauge theories in mind. So many of you may have heard of quantum chromodynamics. This is something somewhat similar to that, but not exactly the same, which I will explain. And so in this class of theories, when you decrease the energy, the coupling will grow, which is completely opposite behavior from this coded coupling in lambda. Okay? So when energy becomes higher, this gauge couplings will tend to be smaller. That's how it works in this kind of field. Now, what does that mean? That means at low energy, you start having bounced in this field. Yeah? And suppose you keep lowering the energy, and at some energy scale, the gauge coupling becomes strong, and then typically bound states will be formed at that energy scale, right? And this typical energy scale will give the typical bound state mass, which I call lambda b. And the quantum wavelength of the bound states that's formed is typically of 1 over lambda b. This is the size of your bound state. Now, we know that these bound states have not been found, right? Because we have only seen the Higgs. So it's better that this lambda b is above where the experimentalists have searched. Okay? So it has to be bigger than 2 TeV, of course. And we don't want it too high, okay, for the reason I will explain. And therefore you expect that this lambda b, which is like between 2 and maybe 10 TeV, you have quite a lot of bound states of, bound states generated by this new strong interacting system. Now the problem is, where is Higgs? Okay, you notice that the Higgs is only 25 GeV, which is a lot lower than this lambda b. So that's the first issue in this class of model building. Why is the Higgs so light? Okay. Again, we will resort to the help of spontaneous symmetry breaking, because we know that once you have spontaneous symmetry breaking, you have Goldstone bosons, as I explained earlier on in this talk, and these Goldstone bosons are massless to start with, okay? And therefore, they will stay naturally light compared to all the other bound states. Okay? So as I said, in this talk, I will first concentrate on the composite Higgs. There's something else called digital Higgs that I will not to I will not have time to cover, but I have some backup slides for this theoretical Higgs as well, if someone's interested. Okay, that's the first issue. Okay, so the general idea is that I treat Higgs as a ghost law, right? You remember that this is different from the Higgs mechanism because the Higgs mechanism is really longitudinal. It's not a ghost law. Okay, but in this theory, Higgs is a ghost from the start. Now the second issue is the standard model fermion mass. What do I mean? Now, in the standard model with the Higgs potential, you know that the Higgs will couple the fermions through the Yukawa coupling to give fermion masses. So to completely replace the Higgs, you have to be able to explain the fermion mass as well. And that leads to some problem. The problem is, so say for example, if some kind of new interaction is emerging at something called flavor scale, which I put it as a pretty high scale. The reason why I have to put it high is because there's something called flavor changing neutral currents in particle physics. That means there are some decay processes, like if you think of quarks and leptons, the quarks will change species, like B quark will go into U quark, okay? Which is not an FCNC, but if you have a B quark going into the S quark, then it's FCNC. And these kind of processes are measured to be very small. And it's the standard model, it was explained by this Kobayashi Matsukawa matrix. Now, in this class of model building, you would like to suppress these class of interactions as well. But if you really look at model building, if you have this kind of operators, this is one example of the operators which may give you the mass terms of the standard model fermions, which are denoted by psi Sn, and this F is actually the fermions which appear in the new strong interaction, or the new strong interaction theory. There's nothing that will prevent you from writing down this kind of full fermion operators, which can lead to flavor changing neutral currents in these kind of theories. And then if you evaluate matrix elements, quantum mechanics matrix elements of all these operators, the size of these matrix elements will turn out to be roughly at a scale, at an energy scale where you evaluate them. So in other words, if you place this lambda f to be very high, and when you run down to low energy where you do your experiments, the effects of these guys will be suppressed, right? So for example, if you do that, they're both very small, so you manage to suppress FC and C, but this becomes too small. So for example, the top quark mass cannot be explained. No good at all. So what do you do? Let's try it. Again, these two operators. One is for the mass generation, and the other one is for the flavor changing neutral currents. You want to suppress this, you don't want to suppress it, you want to enhance this. What if the suppression of one of lambda f square, for some reason, becomes one over lambda that is less suppressed? And it runs down, they run differently, and then it goes back again to this. And then you see, now this is highly suppressed, this is less suppressed. And that gives a successful story. Okay? Now the question is, how does this happen? How does this happen? This flavor scale suppression for this mass operator goes from 1 over lambda f squared to 1 over lambda f. The only way this can happen is that when you change the energy scale where you evaluate the matrix elements of this operator, this f bar f would actually change with some power law correction, which will in turn correct this guy to be 1 over lambda f. Okay? So this is a generic statement. Okay? This is a generic statement. Of course, there will be a lot of details to fit in if someone's interested. Now, you see this power law scaling for condensed matter physicists, they know this very well. This means whenever you see this, you know that the theory of the system is close to, or exactly at the critical point. In other words, the story I showed you on the previous slide could happen if at a big range of coupling values of coupling constants or scales, the system actually is at criticality. Then the story can work. Okay? And let me also remind you that this is very similar, or somewhat similar to this Berdinsky-Kosterlitz two-layer phase transition. Okay? In other words, the theory will actually flow into some criticality regime and stay there for a while, or at least this theory has to be close to criticality for a while, for a big range of parameters. Yeah? So if you can devise this kind of theory, it works. So these are the generic considerations. Let me be a bit more precise, a bit more detailed. So let's start from this analogy with quantum chromodynamics. We know that in quantum chromodynamics, the bound states are formed generally at this 1 GeV. And because the interaction becomes so strong and low energy and induces a spontaneous symmetry breaking by forming this vacuum expectation value of the quark anti-quark pair, and therefore you have Goldstone bosons, which are pions, which are massless. Yeah. Now, but we know that in the real world, these pions are not massless, right? And that's because in addition to QCD, you have electroweak physics. Once you turn on the electroweak physics, and it couples the pions, and then since the quarks will get a small mass from this electroweak physics, then the pion becomes massive. So the mass of the pion is actually from electroweak physics. It's not QCD. It's something above there. It's just something that's happening at higher energy than this bound state energy in QCD. So that's the idea in composite Higgs.
Then David, there's
Yep.
one question here.
Yep.
So you are at the beginning you motivated by this. Then you are saying you want to search for a theory which solve the SM model,
Yes.
standard model problems.
Yes.
But then now you started with a theory. It's already you know it's another renormalized one. So about that, what is that? And then you want to do the lower one. Okay. So then what is the improvement? You got the problem shift from here to higher.
Well, I think, yeah, you're right. The problem is the following, right? I mean, if you think of this, at least in QCD, we know this. You can imagine that we don't have good enough facility to find this weak interaction yet. But at least you can actually have a meaningful theory called QCD, and there you can actually push the cutoff effect to infinity, and QCD is still valid. So at least you succeed in evading this problem of triviality by saying that it's actually we actually have a theory that's not just renormalizable, but you can actually manage to push the cutoff to infinity. And then the question is how I'm going to generate this small mass for the pion, and that's actually something that the phenomenologists are actually working on, and to try to devise things that can be tested at future collider accelerators as well. Yeah, but I think the point is that we deal with one thing at a time. We deal with at least something at low energy, and we can actually meaningfully say that this low energy object is actually replaced by something which can actually have a meaningful limit where I push the cutoff to infinity. That's step number one. That's the philosophy. Okay, so now this is the story about QCD and pion mass. The point is that here at low energy, around Higgs mass, if I insert this story into this area, then it looks like that. Okay? So this is the spontaneous symmetry breaking will give you again Goldstone bosons, and Higgs is one of them. And then once this system is coupled with some flavor physics model, and then this can actually lift the Higgs mass from 0. And some people actually, just to say one or two more sentences about Xiaogan's question, some phenomenologists are actually not happy with this, just like you, right? So they were actually arguing that if you just couple these guys and the Goldstone here to the standard model itself, the feedback from the standard model itself to the composite Higgs zeta will generate a Higgs mass already. Okay? Now, this is actually going to the point that I'm going to make. There are all these classes of phenomenology model construction is going on. So where can Lattice play a role? Lattice studies, of course, can give you the spectrum of this noble gauge theory, right? So it tells you if someday you find something at 40 eV, you find some new states at 40 eV, do they actually fit in the description of this? Or can this kind of model describe this newly discovered or possible resonances out there? And Lattice study can also help you to understand this. This is Xiaogan's point that the coupling here will involve a lot of quantum mechanics matrix elements, and the states in these matrix elements are actually bound states, and therefore normativity studies will be necessary. Okay, and what's even more is that, as I said, you would like to put this theory into criticality in a big range here, and Lattice can actually help you to map out things like the critical exponent and all these things to tell you more about the scaling behavior of all these operators. This is actually a new research direction. As I said, the other scenario, Dilaton Higgs, has been going on for quite a while. But today, I rather concentrate on something that's new, and more things will have to be done in the future. So that's why I introduced this to you. And so at the moment, since this is a new direction, the Lattice studies have actually completed quite a bit of things in this regard here. But these things, these two, remain to be done. Okay? So I think I will just give this I mostly explained already along the way. Oh, except for one point, that to generate the fermion mass, you would have to compute a spectrum of baryons composed of composed of fermions in different representations of the gauge group, and then the mixing between these baryons and the standard models at the top quark would actually give the top quark masses. It's a bit like the seesaw mechanism in neutrino physics. Okay, so the spectrum of these baryons will become important. That's where Lattice can actually do for you as well. So let me then give you the status of this line of research. This is in our group. Well, it's a collaboration that I formed with colleagues in South Korea and the UK. We've actually managed to run a lot of numerical simulations to map out the spectrum of this symplectic SP4 gauge theory, and this is one of the viable or the most promising gauge theories which can be used to construct composite Higgs models. And over the years, well, we've been working on this for 3 years. And on this slide, I show this is the pion mass, and you see that you can regard this as the input fermion mass. You know, it's just a way to plot this fermion mass. And these are all the states like the pions, vector bosons, and scalar. And you have two types of things because we put, for example, you look at the vector, you have a lowercase vector, capital vector, because we put these fermions in different representations. The capital V means vector meson made of two fermions in a fundamental representation of the gauge group. And lowercase v means the same thing, but made of to fermions in the higher representation, call it antisymmetric representation. But the gist of this plot is to tell you that if composite Higgs phenomenologists come to ask us, can you tell us if my model is correct, what are they going to find? And you actually see this, okay? And the black things are just the blue ball. The blue balls, you should look at these. These are the spins of the blue balls, spin and parity of the blue ball states. We've also managed to compute all the blue ball states here as well. Okay? So, I think that's more or less what I want to say about composite Higgs as well. Any quick questions? Because I'm going to change gear for the last 5 to 10 minutes.
So problem is, how do you generate the fermion mass again?
Oh.
You spend amount you cover.
So the fermion mass is generated by having this variance. So this f, little f, is the fundamental fermion. Fermions in the fundamental representation, say, of SP4 gauge group.
Okay.
Capital F is in the antisymmetric representation. Okay? And the antisymmetric representation will give you 2 indices, right? So that's why you can make up a hypercolor neutral state. Okay? And then you put this operator together, say with the top quark mass, and that becomes a 4 fermion operator. And that actually generates mixing between the top quark and this barrier state. And that gives you the top quark mass.
What about the other parts, the other fermions?
You will have similar things, yes. You will have similar things. In this picture, of course, you can think of other models which would actually treat different standard model fermion masses differently. That's of course, is a possibility as well. Yeah.
So what is the special thing about the SP4 which you claim to be easier to calculate? So we know
it's not easy to calculate. It's easy to build a model.
So we know SU3, the color symmetry, electrodynamics. We still don't trust many of the calculations. For example, the global, for example. Yeah. So what is special about the
SP4?
Okay.
So
you
okay. Very good. Very good. So to make a long story short, I can explain to you in detail later. Because this is
just the general.
Yes. Because SP4 is a pseudo-real gauge group. So the group representation is different. So number one, you can actually generate a scalar ghost rather than pseudo-scale. So that's important for Higgs physics. And if you have SP4 gauge group, and then you introduce 2 copies of Dirac fermions. And because of all these pseudo-reality properties of the gauge group, you can show that you actually get only 5 copies, only 5 boson bosons. And that's the minimal thing that you can do in this composite Higgs model building. So if you have 5 boson bosons, and you can actually try to couple to standard model or other new flavor sector to lift up the mass of one of them, and then you still have 4 of them, 4 boson bosons, which you can identify as the complex scalar doublets to replace the same thing in the standard model. So that's the story. So this is the easiest, this is the minimal construction of the composite Higgs model. But unfortunately, it's symplectic. When I first came to this game, it was like, I didn't even study symplectic group before, right? Yeah, but phenomenology-wise, actually, it works the best. Yeah. Yeah. I mean, I can discuss with you for more details later. Yeah. So let me change gear of this talk. So I can have, what do I give, 10 minutes? 5 to 10 minutes? Yeah, I try to finish in about 5-6 minutes. Yeah. Technique for the future is the networks. So this is what we lattice field theorists just picked up from this model theorists. They've been doing this for more than a decade. We just started doing it a few years ago. Okay? And in particular, I like to the things that I'll talk about is the matrix velocity. So the motivation of this is, remember that we want to put this system into some criticality in a big range of parameter space, and it looks like BKT phase transition. You know, this I will show you that this actually gives you very interesting insights. So the logic flow of doing this calculation is that no more path integral. Okay. Some of you may know that the path integral calculations for on lattice is ugly because you have sign problems and blah blah blah, all these shortcomings. And so we want to do something else. Now, logic flow is that we formulate our lattice field theory into Hamiltonian formulas, canonical formulas with many operators. Okay? We go back to operator formalisms and look at Hamiltonian and we turn it into a quantum spin model. This is something like, rather clever. Okay? But we now have some standard techniques like the Jordan-Wigner transformation to work out some of the models. Okay? Generically, I think the research here will still have to be done. In other words, the question is every field theory, is it possible to turn every quantum field theory into a quantum spin model? No, we don't have a definite answer. For many, we do. Now then, once you have the Hamiltonian in this quantum spin model, you can prepare something called metric Porter state, and you can actually use the quantum states, which is quantum Hamiltonian, compute matrix elements. Once you have the Hamiltonian matrix elements, you can actually perform a variational search for the ground state, and that enables you to compute the correlators and matrix elements you're interested in. Now, why? As I said, mapping field theories on the quantum spin models and offer you new insights. That's what I would explain in 3 minutes. Yeah? And also, since we're actually dealing with quantum spin models, then this is a possibility for future quantum computers. Now, what's a matrix Porter state? If you have a quantum spin state like that, and composed of n spins, and to specify this state, you need this coefficient C, J, J, and suppose if locally the Hilbert space size is D, then you see that this is a very large system. The Hilbert space is D to the power n is exponentially growing. Okay? Now, you cheat first by rewriting this as these little tensors, where you have this so-called bond dimension as capital D, and then you say that I can actually replace this guy into the product of all these little a, and then this of course is turned into D times capital D squared and n of them. So it looks like it's a polynomial problem. But of course, as I said, this is cheating because capital D, once you have more and more spins, capital D grows exponentially. Okay? The beauty of this matrix Porter state is that it shows you can argue that if you want to look for the Porter state, you can actually use an entanglement-based argument to truncate this D. The capital D doesn't have to be too big. Okay? You can actually throw away some small entanglements in your system. And therefore, that reduces the problem size. And then you can write this quantum state in this representation of all these tensors. That's why it's called a tensor network. Now, once you have the state, you can also write Hamiltonian as a product of operators. And then you can actually just contract these tensors to compute the matrix elements, and then you do your variational stage. Now we have applied this to 1 + 1 dimensional theory model, whose action is here. So I don't have time to explain details, but let me just tell you that if you plot the phase diagram of this theory model, it looks like this is M, this is G. G is the four-formula coupling here, and M is just the mass term. And then perturbation theory tells you that this operator actually becomes irrelevant here. The RG flows will go to 0, and so you have a critical phase here, and on the other hand here you have a gap phase. And this is a BKT phase transition. Now, what would you do to identify this phase in this case? Of course, you say, it's 1 + 1 dimensional quantum field theory, turn into a quantum spin chain. In this case, it's a 1-dimensional x-exact quantum spin chain with constant and staggered external magnetic field. And we're not discretizing the time direction anyway, so that's why it's a 1-dimensional x-exact chain. And then you just use what I described, and then you say, once I find the ground state, I would just study some commonly studied correlators in quantum field theory, and I write it as these common spin chain correlators, and then I look at these correlators, and I look for the potential law or power law decay, and then I know which phase I'm in. But it's actually not easy to map out the phase boundary, because this is a qualitative state, right? Power law exponential. It's qualitative. How do you know that it's changing from power law to exponential, especially when the data is not actually perfect? But then if you look at this common spin model, there's something called the string correlator. It looks like this. This the Pauli measures in the z direction. You have 0, 1, 2 to r sites. So when r goes to infinity, condensed matter physicists know that this string correlator goes to 0 at criticality, and it is non-zero. It turns into a constant in the gap phase. And this corresponds to this density operator at each lattice site. So field theory. In quantum field theory, at least I never thought about studying this kind of object. So this is something that we picked up, some insights we picked up from spin model. So this is the point. Yeah? It offers something interesting. This is more quantitative. So we use this and we map out the value of this guy at this r equals infinity. This is in collaboration with some quantum information theorist and Inge, which is the room here, and my students as well. And you see that this is again M, and this is coupling 4-photon coupling G, and you see that this correlator can actually give you some more quantitative description of where the phase transition may be. Okay, and indeed using this, we can actually successfully map out the critical phase and massive phase. And of course, this is an exploratory study, so our data can still be improved. So there's a regime where we can still improve our data. And this gray area is a bit ambiguous regime. And so compared to what perturbation theory gives you qualitatively, you see it's actually, it shows the validity of these calculations in our field theory study. So the conclusion for this talk is first, the strong dynamics can actually play an important role in the search for physics beyond standard rule. I hope I at least make that point clear. And lattice field theory, of course, is the most reliable tool for non-interpretive physics calculations in quantum field theory. And here, inspired by looking for BSM physics and facilitated from our interactions with condensed matter theorists, new things, new feedbacks into our own field are also happening. So we're actually having a lot of interesting time, and we have a lot of fun doing this as well. Thank you for your attention. Thank you.
Okay. Bob.
So if you go back to the previous slide, so these on the right hand side, so you choose point to point to the calculation. But then in the perturbation theory, give you those curves. Can you actually get curves roughly or
no.
anything?
Not in our study. Good. So in our study, we're just looking at the correlator, the behavioral correlator, to see if the system is critical or gapped. But in perturbation theory, these curves correspond to the flow in the renormalization group equation. In principle, on the lattice, you can do this, but that requires another technique. I mean, you can, because in the end, lattice renormalization, you can actually have some scale to probe the system and to try to follow the change of the scale on your lattice, right? So say, for example, you can actually use the lattice spacing as your scale to probe the system and change lattice spacing while fixing all the other parameters and see how the system will change, and you identify that as the renormalization group scale, then you can do this. But that's not what we did so far. Yeah, but that can be done. Yeah.
So you mean it's a different dimension of those points? In some sense, because you're going to change the lattice spacing.
Right. Yeah. But I think that if what you're asking is the comparison between these two, I mean these curves here clearly tell you that once you go to low energy of the theory, the mass parameter has to go to 0. And therefore, there's no mass. And therefore, the system is criticality. And that's what we found by using this correlator as well. Yeah.
Hi, David. As a phenomenologist. So,
Okay.
So when I heard about the Lattice, you always think you guys trying very hard to give us some numbers for QCD, and then we can do. I noticed you were involved in the early days in this type of thing, but now today you give the talk totally shifted to the new, the understandable model part using the Lattice part. So there's nothing interesting there at the QCD. Yeah. So I didn't even mention that.
I'm really sorry. I didn't mention QCD as an analogy. It's just I don't have time to talk about QCD studies. Thank you for the question. There are many interesting questions in QCD, and I'm pretty sure you heard a lot from Junwei as well. So, like for example, the hadron structure problem, like the proton structure, we actually have new methods for computing proton structures. Junwei has been involved in very good collaboration on this subject. And I'm also working on similar things as well, just collaborating.
So it's still part of your.
It's still part of my
active interest.
Sure, that's actually a big part of my activity as well. Yes, but just today I don't have time to introduce those activities. Yes.
Composite figures. What's the ingredients of the
Okay,
composite?
good. So you mean the ingredients in your Lagrangian, and then that's you just have fermions and.
2 fermion.
It depends on the model, of course. The model I introduced will actually contain 2 copies or 2 flavors of Dirac fermions coupled to the sp4 gauge theory. Yes. To start with, and then you have to introduce this more complicated.
2 fermion. 2 fermion composite figures.
Yes, they form bound states. Exactly.
2 fermion.
Yes.
Or 2 bosons.
2 fermions. Yeah.
2 fermions.
Yeah. Because Higgs is like a boson. Yes.
For this model,
Yeah.
it has been mapped to a spin system. Do you think there's a advantage of using a quantum computer to do this simulation?
Yeah, because these tensors. Okay, I have to take a disclaimer. I never worked on quantum computing. Okay, so my understanding is that these guys, they look very similar to these quantum computers. So it's actually very natural to port this on quantum computers. But the problem is that in looking for the ground state, we use variational research. There are actually some non-unitary operations are involved. So that aspect cannot be ported directly on the quantum computer. Yeah, but the general formulation itself looks like something we can actually write for quantum computers.
But if you can already done it using a classical computer, perhaps there's not much advantage using quantum computer in this space.
Yeah, but it can be, but quantum computers will be more faster, and it probably allow us to do more complicated studies. Because this on the classical computer it takes time. Yeah, it takes quite a bit of time to do the simulation, although it's a one-dimensional system.
Okay, anyone? Anyone else? Okay, if not, let's send the speaker again.
Thank you very much.